Hello AP Precalc kids, this is Mr. Bean. I'm going to fill in for Mr. Brust for this very first lesson of the last half of Unit 3 on the tangent function today. Mr. Brust will cover the rest of Unit 3. I'm just doing this one lesson here, a little cameo here. So I want to remind you when we get into tangent, if you remember the SOHCAHTOA stuff, remember that? Tangent is the TOA. So that is where we have opposite over adjacent. And if I were to draw a quick little triangle, right triangle, where we have theta there, then it would be the opposite divided by the adjacent. Now I'm just reminding you that really fast so you can see how this fits in on a circle, on a unit circle in particular. So if we take a ray, so draw yourself a quick little ray here, and it doesn't really matter. It can be exactly like mine if you want in that angle. And if we just put this ray anywhere, somewhere in here, and then we're going to label the point of intersection on the circle itself as P, so we'll call that P, then we have the ability to figure out for this angle here, so this is the standard position angle, theta, then tangent is the opposite, in this case, this y value here, divided by the adjacent, which in this case is the x value. So if we have y divided by x when we're doing this on any line, that y value divided by that x value from the origin, that gives us slope. So tangent is the slope of the terminal ray on a circle. So if you draw any angle in standard position, then the tangent of that angle is actually the slope of that terminal ray. Okay, that's an important thing because that's the way some of the questions will be phrased, as they say, find the slope of the terminal ray. You have to know that just means you're finding tangent. Okay, so now another thing is the slope of the terminal ray can also be described by the ratio of this change in y over change in x. You can also think of tangent as the ratio of sine and cosine. Therefore, we have tangent theta equals sine theta divided by cosine theta. So that is a quick way of being able to figure out what is tangent. It's, if you know sine and you know cosine, you just do sine divided by cosine, as long as cosine does not equal 0, because if cosine equals 0, denominator would be 0, and then the universe blows up, and we can't do that. So tangent would be undefined. Okay, so moving on. Let's put it into practice. So here we have a problem that says in the xy plane, you've got an angle theta in standard position, and the angle has a measure of pi over 3. What is the slope of the terminal ray of the angle? So when you see that, what's the slope of the terminal ray? It just means what is tangent. So I drew myself a quick little circle, put it on a coordinate grid, and then just think, where is pi over 3? This is just to help remind us which of these three dots is pi over 3. It's the top one there. It's this third one. So what is the coordinate point of that pi over 3? That coordinate point is 1/2, comma, square root of 3 over 2. So if we know the coordinate points of these angles on a unit circle, that will help us quite a bit, because then all we have to do is say that this is going to be the sine value divided by the cosine value. Or in this case, it would be the square root of 3 over 2 divided by 1/2. And whenever you have these, you notice how you're going to have these 2's on bottom, the 1/2s. Those 1/2s will cancel. And so all you're going to have is the square root of 3 over 1, or in other words, square root of 3. So the slope of that terminal ray right there, that terminal ray slope is the square root of 3. Okay, next up, we're doing exactly the same thing. So finding the tangent values is the same as finding the slope of the terminal ray. These two things mean exactly the same thing, it's just worded differently. So if you see evaluate tangent of an angle, it's the same thing as saying what is the slope of the terminal ray. All right, so let's do this one together real quick. What is the coordinate point of pi over 4? So that is going to be square root of 2 over 2, comma, square root of 2 over 2. So if you can write down the coordinate point, that'll probably help you quite a bit. And then you're just saying, oh, well, that's just the y divided by the x, square root of 2 over 2 divided by square root of 2 over 2, that equals 1. Super easy. Okay, 5 pi over 6, where's that one? 5 pi over 6 is right close to there, somewhere around there, something like that. It's almost at pi. So that is negative square root of 3 over 2, comma, and then what's the y value? 1/2. Then we're doing y divided by x. So we get 1/2 divided by negative square root of 3 over 2. And then that's going to equal, the halves just cancel, so all we have on top is a 1 divided by negative square root of 3. Now this is a correct answer, 1 divided by negative square root of 3, or just negative 1 over square root of 3. But if it's a multiple choice exam, often they may just rationalize this. So they would multiply top and bottom by square root of 3 to then get a negative, the negative is from right there, square root of 3 over 3. That's how you rationalize these fractions. Again, this answer right here is correct, but you want to practice rationalizing just in case you don't see, if this might be the answer on the multiple choice and you think this is the answer and you don't see that these two things are equivalent, then that's a problem. You just want to know that these two things are equivalent. Okay, next is tangent of 3 pi over 2. Where is 3 pi over 2 on the unit circle? It is right there on bottom, 3 pi over 2. And so what's that coordinate point? That is an x value of 0, a y value of negative 1. And so then we're going to have negative 1 over 0. Uh-oh, that is undefined. We cannot divide by 0, so tangent at 3 pi over 2 is undefined. Nothing there. All right, that's how we find the tangent values. That's how we find the slope of the terminal array. So let's now move on to some other stuff. All right, here we're gonna get ready for what in the world is tangent doing? Like, what's the graph of it doing? Let's start with a unit circle. I'm gonna take this terminal array and I'm gonna rotate it around the unit circle just to get a feel for what tangent is doing. So remember, tangent is the slope of this thing. So what does the slope start off with when we're in standard position? Right at the very beginning, the slope starts at 0. Slope of a horizontal line is 0. So now as we start moving around the unit circle, what's happening? The slope is positive, and the slope is positive, and more positive, and more positive. It's getting really, really steep. What's happening to it? It gets larger until it approaches infinity. It's approaching infinity as it gets bigger and bigger and bigger and bigger until we get right to pi over 2. And now all of a sudden you have this vertical line. What's the slope of a vertical line? Undefined. So we'd now have undefined there. Then what happens next? As we keep going, the slope right there, as we pass that point, the slope is now negative. And that's getting less negative, so the slope's actually getting larger. So it was super negative, and it's getting larger as we get towards 0. Once we reach right here, what is that angle right there? That angle is pi. So once we get to pi, we are now back to a slope of 0 again. And then we're going to keep going. And so as soon as we pass that, what is happening? We have a positive slope. The slope will be the same as it was in quadrant 1. This is now the same slope. Now you can see here, if I extend this line, you can see that would be the same exact slope as when I was way over here in quadrant 1, and it's just going to now repeat itself. So if I keep going around here and I get down, it's the same as when it was way up here in quadrant 1. So it's a repeat. So once I made all the way here to pi, it's going to start over and do the same exact tangent values again. And then it's going to start over and do the same tangent values. So how often does that happen? Every 1/2 revolution, every half of a circle. That's when the tangent function repeats. So the period of tangent, how far did we have to go for the period? The period is only pi. Not like sine and cosine. Sine and cosine was 2 pi. You had to go a full circle to get a repeat values. Tangent, you only have to go half a circle, and then it starts repeating again. So period of tangent is pi. Now, one thing is, remember how we had this undefined thing? So where did the undefined slopes happen? It happens when cosine is 0. So that's my next part here. Cosine theta equals 0. When does that happen? It happens at these angles. Pi over 2, and then it happens again at 3 pi over 2, and then it happens again at 5 pi over 2, and it just keeps happening in that, but you just add pi, add pi, add pi. So we're going to have a way to say that here in just a minute. We'll talk about that. But that is going to be where our vertical asymptotes are. So what you're going to do now is you're going to sketch some vertical asymptotes real quick that will look like this. There's one vertical asymptote right at pi over 2. Yours won't look as cool because it won't be red. And then, well, maybe some of you will. And then we're going to do another one. Where's the other one? At what? 3 pi over 2. And so notice that we have a repeat every pi values. I could go the other way to negative pi over 2. So these are all the places where cosine is equal to 0. and cosine being 0 causes tangent to be undefined. So there's our vertical asymptotes. So that's an important thing for you to see where these vertical asymptotes are. When we start sketching things, you're always going to start sketching the vertical asymptotes first. If you can't do the vertical asymptotes, it's going to be really hard to sketch the graph of these. All right, so then next up, where are these vertical asymptotes? Well, this is how we say that. They appear every pi over 2 plus k pi for integer values of k. You might, sometimes teachers or books will say n pi. It doesn't really matter what that variable is, that value is, as long as they say the same thing. I think Mr. Brust in his lessons is probably going to change it to an n. Don't freak out about that. It's the same thing. Okay, so k, pi over 2 plus k pi for integer values of k. So let me go back there. So that just says we're at pi over 2 and we're adding a pi. We add one period to get all the other vertical asymptotes. And you just keep adding periods over and over again. But what if it's not tangent theta? What if it's tangent b theta? Like there's a little constant in front of theta, a little coefficient in front of theta. Then it changes the period. The period is then pi over b. That's the period of tangent where you have a coefficient here. Please don't get this confused. Remember when we did sine and cosine? Sine and cosine was 2 pi over b. We've done that a whole bunch for sinusoids. Do not get that confused with tangent, because with tangent, it's not 2 pi over b. It is pi over b. You've got to be able to interchange between the two of them, knowing when you're dealing with tangent, when you're dealing with sine and cosine. Periods are different. Okay, so if you have this tangent of b theta, then that's going to change how often you have your vertical asymptotes. I'm going to explain this a little bit more here in just a second. So just get this written down, and then when we practice it, it'll make more sense. So here's these two things here. The vertical asymptote is going to appear at every pi over 2b. So it's going to actually be half of the period is where the first vertical asymptote appears, and then it's going to repeat every period. So it's just k times a period. Pi over b is the period of tangent. So it's integer values of k. You just do multiples of the period. All right, that might seem a little confusing. Let's just do a problem real quick here on here. And I think this will make sense. Okay, so the period, what's the period for this thing? The period is going to be pi over b, which is 2. So if I have, I'm going to sketch this real quick. If I have my vertical asymptotes surrounding the origin here, the tangent's going to be right in the middle of this, in between these. Where are these vertical asymptotes? Well, if the entire period is pi over 2, that means this distance right here, right there, that distance is half of pi over 2, which is pi over 4. So we have vertical asymptotes. I'm going to just abbreviate this by saying vertical asymptotes at x equals a positive and a negative pi over 4. That's where the vertical asymptotes are. So we're going to then say, here's our formula. We say the vertical asymptote is at pi over 4. It's our first vertical asymptote. And then we're going to add every period as another one. So we say k pi over 2 for integer values of k. All right, that right here is the whole answer. That whole thing, oh, squeezing it in. Oh, I almost crossed that off. That whole thing is the answer to this. There's our little formula, pi over 4 plus k times the period. So we start with the first vertical asymptote and we just add periods to it. And that gives us all of the vertical asymptotes for that function. All right, let's do another one. So here, what's this one? The period is going to be pi over b. In this case, b is 2/3. Well, that makes this multiplied by the reciprocal. We get 3/2 pi. So again, what are we doing here? We have vertical asymptote there, a vertical asymptote there. That whole thing is 3 pi over 2. So half of that, where's this first, that distance from here to here, that distance is half of a period, which would be 3 pi over 4. Okay, that's where that comes from. So then I can say, all right, so I've got a vertical asymptote at x equals, there's a positive 3 pi over 4. I can just say 3 pi over 4. Sometimes you might say plus or minus because that one represents the negative one. But I've got one of them at 3 pi over 4. So then I can say my answer to this is that I have a vertical asymptote at 3 pi over 4 plus a period, which is 3 pi over 2. So plus every k, 3 pi over 2. Every period where I'm multiplying it by k for integer, I can't write, integer values of k. There we go. And then box that. kind of a box. That's awful. All right. There's our answers for how to do those. Hopefully that makes sense to you, because you will have some problems on that, and you'll see some of those in AP Classroom as well. Okay, now let's talk about some characteristics and get to the graph of these things, because I know you love graphing. All right, characteristics of the tangent function. This is what it looks like. This is the original parent graph of a tangent function. So you see here, I've got my tangent down here, and what is happening? Each time between these set of asymptotes, after we figure out where the asymptotes are, the function is always increasing, right? It's never going down here, it's just always going up. And then its graph is going to change from concave down to concave up. So notice this is concave down, and then right here it changes and it becomes concave up. And that happens over and over again, it repeats itself. That point where it changes concavity, that is, remember, that's called a point of inflection. That point, I'm going to fill in as a dot, is really important, because we first find the vertical asymptotes, and then we find the point of inflection when we're trying to graph these things. Vertical asymptotes, point of inflection, and from there we can sketch the graph of it. So those are the important things of being able to look at these graphs. All right, with that, we don't just have a whole bunch of really easy graphs though, right? We're not going to graph tangent theta over and over again. We're going to do things to it. We're going to multiply it by a number in front, multiply the theta on the inside, add or subtract something to it, and then add something at the very end. We're going to have all these different transformations of the original function. So what do all these things do? I think a lot of this you're going to already be able to recognize, because it's the same thing we've been doing with all the different types of functions. So what's A do in front? It creates a vertical dilation. It stretches it up and down, or it shrinks it up and down. So it stretches or shrinks vertically by a factor of the absolute value of A. Now, if A is negative, what's it do? It flips it, right? So there's a reflection over the x-axis. Okay, so those things, nothing new there. I will talk about A again when I get to the graph. I'll talk about how A is also helpful on the graph. Constant B, what's that do? The B on the inside, that gets a little bit trickier. That creates a horizontal dilation, right? And it's always the opposite. So it changes the period by a factor of 1 over B. So if B is large, the period shrinks. If B is smaller than 1, like between 0 and 1, if it's a small number, the period actually grows. So it does the opposite of what you'd expect. And if B is negative, if B is negative, there's a reflection over the y-axis. It flips left and right for the reflection process. All right, constant C, remember this? So that we have a plus C on the inside. That creates a horizontal translation. We're now shifting it left or right. And it's always the opposite. So in this case, if it says plus C there, it's a minus C. So nothing new here. We've been doing this stuff over and over again. And then the constant D at the very end, this plus D, it's going to create a vertical translation. It's shifting it up or down by D units. Okay, so now we're going to take all this information, put it to use, and graph. Here we go. What should we start with? There's all these things going on. We need to know where the vertical asymptotes are. Identify the vertical asymptotes, shift them according to any shifts that we have for phase shifts, and then we can get points of inflection. So vertical asymptotes, we've already practiced this. Let's take the period, figure out what that is. So the period is going to be, oh, wait. Sorry, if you already wrote that, let's do something else first. Let's take this 2 and factor it out so that we can see what the phase shift is. So 2 times theta minus, this just leaves us with pi, right? No, that's wrong. So theta minus, what is it? Oh, pi over 4. Oh, that was tricky. Yeah, because now if I distribute the 2, I would then get back up here. All right, so now that helps us with the phase shift. So now let's do the period. The period is pi over b, not 2 pi over b, just pi over b, in this case a 2. So if we have that, that means I have a vertical asymptote at half of that, right? So I have a vertical asymptote at x equals half of that, pi over 4. So don't graph it. I'm just going to show you where that would be. It would be right there. Again, do not sketch this yet because I want you to see what we're doing. So then from that, what else do I have going on? I have a few things going on. I need to say that it is a shift right pi over 4. So just one line. And then I also have it's going to go up 1. Okay. So here's how we do that. Let's take our vertical asymptote, and I'm going to, now you want to sketch this. We're going to move it to the right, a pi over 4, which is just one line, right? So there I have that. Now where was my other vertical asymptotes. Let me show you. Let me pull this back. The vertical asymptotes would be here and here. Maybe that's how you should be able to see it, because that's a period of pi over 2, that whole period. Positive pi over 4, negative pi over 4, vertical asymptotes. Now we're going to take these and shift them right pi over 4 to there. Almost. Right there. Okay, so now that's where I'm going to take and draw more vertical asymptotes. So it looks like we're going to have vertical asymptotes every 2 lines, which is every pi over 2. So sketch all of those. Okay, that's a lot of vertical asymptotes. Okay, now what? We've got, let's find the point of inflection. So the point of inflection will be right in the middle of these things, but we had to shift it up 1, right? So this up 1 comes into play. So there's my up 1. That's a point of inflections. Go ahead and dot all the points of inflection real quick. Okay, your graph should look something like this so far. That's what our sketch is. Now we're going to remember that tangent is going to go up. It's going to go concave down and then concave up. What I'm telling you here is that the A value helps us with a quick little sketch. The A value is 1/2. And this is kind of a nice little trick to help with the sketch. If you go halfway from the point of inflection to the vertical asymptote, halfway in between, and then you go up A units, which in this case is 1/2, that is actually the value right there. So halfway between the point of inflection and the vertical asymptote, you go up A units. So you can do that real quick. And then you do the same thing the other direction. So you go the other direction, but you go down A units. And so then it would be like that. Go ahead and put those dots real quick. And then from here, it's sketching. Now be careful here. This is not a straight line, right? We're not just connecting these. We want to go on the right side here where it's going up. It's going to be concave up. So just kind of try to make it, if you're any good at it, concave up for each of those. And then on the left side, it's concave down. And you just try to hit that thing, and then the vertical asymptote will push your graph down. So again, it's just a sketch. The vertical asymptotes are very important, and the point of inflection. You want to make sure those are accurate for sure. And then from there, it's just kind of a little bit of a sketch for understanding the graphs. All right, number 8. This would be a really good one for you to pause this video, try this one on your own. I will then have the answer with all the explanation to see if you get the same thing as I do. Okay, how'd you do? This is what it should look like. If you got that, you're crushing it. You're ready to move on. If you didn't get that, just look over what I have. I've got the period here is 2 pi, the vertical asymptote at plus or minus pi, but then I had to, instead of the vertical asymptote being here at pi and negative pi, I had to shift it left pi. So that's why everything shifted over to the left. And then another trick was that there was a vertical, this negative here in front caused it to be a vertical reflection. So it's decreasing instead of increasing for this tangent function. The 3, again, also that 3 there in front helped me with these other coordinate points. Halfway to the vertical asymptote helped me to identify where those other points might be to help with the sketch. Okay, that's everything. This is Mr. Bean signing off. Rock that mastery check. I will not see you back until Unit 4, for those of you who are doing Unit 4. So good luck with Mr. Breast, and I'll see you later.